Hello everyone, I'm Yewei Zhao. It's my honor to introduce our work, Deep Subdomain Alignment for Cross-Domain Image Classification. This is a joint work with Han, Shiguang, Shan, and Xilin, Chen. All of us are from key laboratory of Intelligent Information Processing, Chen's Academy of Science. The deep neural network achieves amazing performance on image classification. Its generalization ability declines significantly on the out-of-distribution data due to the domain shift. Unsupervised domain adaptation addresses domain shift by transferring the knowledge acquired from a labeled source domain to a target domain without requiring any labeled data in the target domain. In existing methods, subdomain alignment methods usually achieve better performance than global alignment methods. Typical subdomain alignment method DSN aligns subdomain distribution based on local maximum mean discrepancy, but it overlooks the stringing of decision boundaries among subdomains, and the subdomain and target domain are then the equal importance in calculating. The motivation of our work are, first, to build firm decision boundaries among subdomains. Second, the memorization strength of DNS towards different instance increases as training progresses. We want to use this property to filter samples, by which we can more fully explore and use the source domain and target domain samples. There are mainly two contributions to our work. First, we propose a novel deep subdomain alignment-based method for cross-domain image classification, which considers not only the subdomain alignment, but also the discriminability and dispersity of subdomains used for alignment. Besides, we design a multi-view subdomain alignment strategy that considers both the target source and target-to-target subdomain alignment to avoid distractor samples in target domain causing bias during adaptation. This is the framework of our method. It consists of three parts: Union Subdomain Contrastive Learning loss, easy sample filter, and multi-view subdomain adaptation loss. This is the Union Subdomain Contrastive Learning module. The purpose of it is to optimize the decision boundaries among subdomains. Inspired by both maximum mean discrepancy and supervised contrastive learning, we calculate the distance of two samples in reproducing kernel-helped space. Then, we use supervised contrastive learning to build firm boundaries in reproducing kernel-helped space. Multi-view subdomain alignment is designed to fully explore and use third domain and target domain samples. It consists of two parts: target-to-source alignment and target-to-target alignment. Target-to-source alignment align target features to labeled third domain features, as the red dot line shows. DCS is the indices of the sixth category in third domain features in memory bank. YIC is the sixth entry of vector YI. We create a memory bank M to store features of source samples with their labels at a maximum size NS. Every mini-batch, source and target samples first go through a network to get their features and predictions. Then, we store features of source domain samples with their labels at a maximum number of NS and drop the oldest ones. WC is calculated following local maximum mean discrepancy to surpass the noise. Target-to-target alignment aligns target features to easy target features, as the blue dot line shows. DCT is the indices of sixth category of target samples stored in the memory bank. At training, target features in the current mini batch also align to easy target features stored in memory bank M. Target samples whose confidence axis HT are denoted as easy samples and will be added into M for subsequent target-to-target alignment. HT is the threshold to filter easy target samples. H high and H low are the high and low thresholds. I iter and n iter are current iterations and total iterations threshold decrease runs. Then the multi-view subdomain alignment loss is the sum of target-to-target alignment loss and target-source alignment loss, and the overall loss of our method is classification loss plus lambda 1 multi-view subdomain alignment loss plus lambda 2 multiple union subdomain alignment loss. We evaluate our method on Office 31, Office Home, and with DA17. The evaluation metric is accuracy. On Office Home, our method accesses the baseline method DSN for 3.3% and outperforms some SOTA methods. On with DA17, the exceeding performance is 3.1%, and on Office 31, we can see that it is 1.1%. For visualization, we draw the TSNE map of both baseline and our method. It's clear that our clusters are tight and the boundaries of clusters are formal. We also evaluate the stability of our method. At the same early stopping epoch, the baseline method suffers a performance decrease of 1.4% on average and 70.7% on max, while our method decreases only 1.1% on average and 3.1% on max. We also introduce the ablation studies of our method. This is a ablation study of our proposed models. From tables, we can see that each of our models is effective and their combination will improve the performance in advance. Memory bank size is a fat vector in memory-sensitive system, so we test the influence of different memory bank sizes of our method. We can see that at an appropriate of 5% source features and 5% of target features, our method works best. The performance won't increase after this proportion. We also evaluate the influence of hyperparameters of lambda 1 and lambda 2. We can see that a larger lambda 1 will make the algorithm works better. In conclusion, first, bringing samples within the same subdomain closer together, while pushing samples from different subdomains apart in the reproducing kernel-helped space is an effective approach in unsupervised domain adaptation. Second, multi-view subdomain alignment strategy that reduces bias in the domain adaptation process by aligning target domain samples to both source domain samples and easy target domain samples using a dynamic thresholding scheme better exploits the source domain and target domain. However, our method doesn't outperform the newest non-statistic matching-based methods, which is the commonality of static matching-based methods. We will further explore the question in the future. Thank you for listening.